Good day, everybody. Today I'm going to look at hopefully a quick proof of the Fundamental Theorem of Calculus, Part 2. So before we look too hard into the definition and the proof, one thing I'll need is a preliminary theorem, the mean value theorem. Simply stated, the mean value theorem says that if f is continuous on a closed interval and differentiable on the open interval, then there is a number c in the open interval such that the slope of the line connecting the endpoints, the secant line, the slope of a tangent will equal that slope somewhere. So the way I wrote it here, it's a little stronger hypothesis. If f prime is continuous on the closed interval, then of course it's continuous on the closed interval as well. Visually, let's take a quick look at what that means. So this will be a little picture of some graphs illustrating the mean value theorem. So I've got it here, kind of zoomed in, or if we zoom out a little, we can see that the secant line is here, and somewhere the slope of the tangent will have to equal that. There's at least one point. So a couple more examples. We've got for sine. So there's the line connecting the endpoints of sine from 0, 0 to pi over 2, 1. So you can find that slope, and somewhere the derivative will equal that slope. Arc cosine's a nice example of a function that would be continuous on the closed interval, but differentiable on the open interval, right? So it's not differentiable at either endpoints, at vertical tangents there. But the mean value theorem will hold. In this case, there's actually 2 points where the slope of the tangent would equal the slope of that secant, sometimes called the average slope. Maybe a couple more quick examples. I think we get the idea, but there's 3 over x and somewhere, and again, so there could be more than 1 point. You're only guaranteed the existence of at least 1 point. There can even be infinitely many points. The function x squared sine 1 over x, with x being 0 at 0, is differentiable on the on every interval, so it's differentiable everywhere. And if I use the mean value theorem on this, say, little interval, then there's an infinite number of local max and mins, which is kind of interesting, but here we're doing it with the mean value theorem. So there's the slope of the line connecting the endpoints, and there would actually be infinitely many places where, and they're kind of isolated. So it's not like a horizontal line segment or any line segment. So they're isolated points where the slope of the tangent would equal the slope of the secant. Infinitely many for any interval containing the origin. So kind of interesting, but not needed in our proof. And I digress a little. So again, there's the statement of the mean value theorem, and we'll use it in our proof. So now let's get to the proof. So we'll need the definition. I'll use the most general definition for the Riemann integral, and that's if you have a function defined on the closed interval and you have a partition, you're going to need the limit as the largest subinterval goes to 0 of that partition. But if the limit as that largest subinterval goes to 0 of f of xi star, that's any point in the subinterval, times the delta xi, that's the length of the subinterval. So if that sum converges to a number, then we'll call that number this definite integral, and that will be the Riemann integral. So a quick look at the definition. I do need one more result that I won't prove, and that's if f is continuous, then it will be integrable. So the integral will exist. So now on to the theorem, the Fundamental Theorem of Calculus, Part 2, it's often called. So if f prime is continuous on the closed interval, then it's definitely integrable, and that integral will be f of b minus f of a. So the integral of a derivative will be the difference of f at the endpoints. So again, here's the theorem. F prime continuous, then its integral will definitely exist. And here's the proof. First, we know it's Riemann integrable, so this limit will exist. Okay, so far so good. Now for each partition of AB, we're going to choose a point in the subinterval so that the mean value theorem holds with f, right? So we're integrating f prime, but we're going to find the point for f prime by going back to f and using the mean value theorem on each of those subintervals, right? So there's some point so that, you know, for the first one it'd be f, if you're going from x0 to x1, then this would be the slope of the line connecting the endpoints from x0 to x1. Somewhere the derivative will equal that slope. There's at least one point. Use that point. So that's how we're going to pick our points in the subinterval. Then if we look at the sum, the Riemann sum here, I can replace this f prime evaluated at xi star with, well, since we chose that point so it satisfies the mean value theorem, this will hold for each of those subintervals. But what does delta xi equal? It's just the length of the subinterval, or in other words, xi minus 1. So this equals that, and it'll cancel the denominator. And we have what we often call a telescoping sum. So if I write out the terms of that sum, the first term is going to be, when I is 1, f of x1 minus f of x0. And the next term will be f of x2 minus f of x1 when I is 2. And when I is 3, it'll be f of x3 minus f of x2, and so on until you get towards the end, f of xn minus 1 minus f of xn minus 2, and then plus when I is n, the last sum there is f of xn minus f of xn minus 1. So I called it a telescoping sum because if you look at it, we've got f of x1 minus f of x0, but then we have minus f of x1 here, and that'll cancel with that one. Then we have f of x2, well, so we already subtracted there, but over here I'll have minus f of x2, that'll cancel with this one, and so on. They'll always be canceling. There's nothing to add to, so this f of x0 doesn't cancel anything, so it will remain. But all these others will end up getting canceled. And then the last canceling will be f of xn minus 1. And f of xn also doesn't get canceled. So what survives is f of xn minus f of x0. But of course, that's just f of b minus f of a. So since every partition where we choose xi star has this limit equal f of b minus f of a, then in particular it's also true for those partitions where the max delta xi goes to 0. So I mean, it's true for all of them. As long as you choose xi star this way, this sum will go to this value. So it's also true for those with delta xi going to 0. And since in general, this is what I wrote here, this limit exists, every way of having the partition must converge to the same limiting value because the limit exists. And so we showed that by doing it with picking xi star from that mean value theorem, we're going to have it equal f of b minus f of a. All the others must go to that same value since the limit exists. So this limit must equal f of b minus f of a. Or equivalently, the integral of f prime equals f of b minus f of a. And then equivalent to that is if f is continuous, then the integral of f, of course, exists, but it'll equal f of b minus f of a, capital F, where capital F is an antiderivative of little f. Or in other words, little f is a derivative of big F. And any antiderivative will do. So hope that made sense. Actually, I do have a little graphic representation of this. So here's 1 over x. Kind of chose some weird limits, but from 0.25 to 2.5. So the antiderivative will be natural log x, and you'll subtract natural log of 2.5 minus natural log of 0.25 to get the exact value. Again, so here's the function for which 1 over x is the derivative, right? Natural log x. So I make that procedure to pick the values of c using the mean value theorem. And so if I only have one rectangle, I mean, it's gonna give the right answer no matter what. So evaluating as a decimal natural log of 2.5 minus natural log of 0.25. And then that's here in blue. But using our numeric approximation, or our Riemann sum with one rectangle, we got the exact same value. And again, so how do I pick that value? If I look at the antiderivative of 1 over x and use the mean value theorem on that interval, there's one point where the tangent, slope of the tangent equals the slope of that secant, and that's the x value I used to evaluate the height for the Riemann sum. I can do it on 3 rectangles, I can do it on any number, but I only did the mean value theorem graph for 3. So here's, again, the antiderivative, log x. I broke it up into 3 subintervals of equal length 0.75, so we go from 0.25 to 1, from 1 to 1.75, and then from 1.75 to 2.5. And on those 3 subintervals, you can see the slope of the secants there, and then somewhere the slope of the tangent will be that same slope. That's indicated there. That's how I'm going to choose the x values for my Riemann sum. Right, so I have both graphed here. There's the 1 over x. There's the above log x with the 3 subintervals and the 3 x values for the mean value theorem. So using those x values, that's how I chose the height of those 3 rectangles. And again, it's going to match exactly. So the approximate value is actually the same value, at least, you know, decimally put to this many decimal places. So again, here it is with 3 again, and it doesn't matter how many I choose. Like if I do 10, I'm always going to get, whoops, that was 103. Well, it doesn't matter, but so I got the same value as what I'm supposed to get. Let me make it 10. And again, so I'm using that procedure. If I change it to some other way, like midpoint or something, it looks similar, but now notice the value is different than the exact value of log minus log. Right, so now there's a difference. And well, one more function. I did the work. Let's make us look at it. So there's the procedure to pick the point using the mean value theorem. So here I have 2 subintervals on x cubed over 6. Now that is not what I'm going to integrate. I'm going to integrate x squared over 2. So this is the f, x cubed over 6. X squared over 2 is the derivative. And so I'm going to integrate the derivative. With 2 subintervals, these will be the 2 points I pick for the rectangles. And you might know the answer. So if you integrate x squared over 2, we'll get x cubed over 6. And we have to evaluate from 0 to 2. And we should get 4/3. And well, we pretty much did. It's a lot smaller picture here, but there's the mean value theorem on the antiderivative. And there's the function. Or equivalently, here's the derivative and there's the function. And again, it wouldn't matter how many rectangles I choose here. Let's do, right, so if I choose 7, again, I'll get 4/3 for the integral of 1/2 x squared from 0 to 2. And x cubed over 6 is that antiderivative. But if I choose some other way of picking the points in the interval, of course I won't get the exact value. Maybe do random this time. All right, so now it's 1.427. So not the 4/3 it should be. But of course, as you go more and more, you'll converge because it's a Riemann sum. So we're getting closer to 4/3 if I use more and more rectangles. But it's always exact if you choose the points as described by that, using the mean value theorem on that antiderivative. And hence, we could prove this result. All right, so hope you learned something from that proof and appreciate it. Thanks and have a good day.